Hello there, Mr. Sutton here, bringing you the BC Calculus 617 Extra Practice Number 3 solutions on Euler's method. On this problem, we're being asked to use Euler's method with increments of negative 0.1 to approximate y when x is 1.7. So basically, we're trying to figure out an approximation for f of 1.7. And we're starting here with this differential equation and also the value f of 2 equals 2. So to do this in increments of negative 0.1, we're going to have to take 3 steps to get from 2 to 1.7. So my first step, I'm going to figure out an approximation for f of 1.9. So that's going to be approximately equal to f of 2 plus f prime of 2 plus my increment now, my step size of negative 0.1. And now let me fill in a few values for this. F of 2, this is actually exactly equal to 2. Now for f prime of 2, we're going to have to use this differential equation. So for f prime of 2, I have an x and a y value I need to plug in. So this is going to be the x value 2 minus the y value, which is also happening to be 2, comes out to 0. So f prime of 2 then is going to be a 0, so plus 0 times negative 0.1. And let's see, that just zeroes that second term out. So our approximation for f of 1.9 is quite undramatically also 2. Okay, now we have to approximate f of 1.8. So that's going to be approximately equal to f of 1.9, which we just came up with a value for. It was 2, plus f prime of 1.9 times our step size of negative 0.1. So f of 1.9, we're using that 2 that we just found. And for f prime of 1.9, now we have the x value 1.9 minus this y value that we just found of 2. So this is going to come out to negative 0.1. So we have negative 0.1 times the step size, which also happens to be negative 0.1. If I multiply those together, that's going to be positive 0.01. So this comes out to 2.01 when all is said and done. But we're not quite there. We have one more step to go. Now we're going to reach our ultimate goal of approximating f of 1.7. And to do that, we're going to take f of 1.8 plus f prime of 1.8 times our step size of negative 0.1. f of 1.8, well, we just found that. That was 2.01. And now for f prime of 1.8, we're taking the x value 1.8 and the y value that goes with it, which is approximately 2.01. So we're going to subtract that. And what is that coming out to? Well, let's see here. This is like having 180 minus 201. This is negative 20. That would be negative 21. This is negative 0.21. So I've got minus 0.21 times negative 0.1. And if I multiply these together, this is basically going to be positive 0.021 that I'm subtracting. Although I take that back, I have a negative times a negative, so thankfully I'm adding that. So we have 2.01 plus 0.021. That's going to come out to 2.031 when all is said and done. You didn't need to simplify for a free response, but it's good practice for multiple choice because they do often expect us to do this without a calculator. So 2.031 is our approximation for f of 1.7. For this problem, they're asking us to use Euler's method with 3 increments of equal size to approximate the value of y when x is 1.7. So we're given this differential equation, x minus 2y. We're told f of 2 equals 1. So we need to get from 2 to 1.7 for plug-in values in 3 steps. That means I need a step size of 0.1, and it's got to be negative 0.1. So that's my delta x as I go here. So my first step, because I have to do this one step at a time, is going to be to figure out what f of 1.9 is approximately equal to. So that's approximately equal to the following here. We're going to have, let's see here, f of 2, which we actually do know the exact value of. And then we're going to have, adding to that, f prime of 2 times our step size of negative 0.1. F of 2, they told us, is exactly 1, so I'll write an equals there. But now f prime of 2, we're going to have to do a little more work for that one. So when I'm plugging in the x value 2, I have to keep in mind I'm also plugging in the y value 1, which is important because this differential equation requires both x and y values. So I have the x value 2 minus 2 times the y value 1. 2 minus 2 just gives us 0. So I've got 1 plus 0 for f prime times our step size of negative 0.1. This zeroes out that whole second term, just giving us 1 for the approximation of f of 1.9. Moving on now, we're going to use this to help us find f of 1.8. So that's going to be approximately equal to f of 1.9 plus f prime of 1.9, the slope there, times our step size, which hasn't changed, still negative 0.1. F of 1.9, we just found it approximately. It equals 1 almost. And then for f prime of 1.9, we have the x value 1.9 minus 2 times the y value that goes with it. Now that y value is this approximation we just got of 1. So 1.9 minus 2 times 1, this is going to be negative 0.1. So now I have minus 0.1 times another negative 0.1. So this is really 1 plus 0.01, which is 1.01. And now we just have one more step. We have to do f of 1.7. This is what we've been waiting for here. This is going to be f of 1.8 plus f prime of 1.8 times our step size of negative 0.1. Well, f of 1.8, we just found that approximately. That's 1.01. F prime of 1.8, now I have the x value 1.8 minus 2 times the y value that goes with it, which we saw was approximately 1.01. So this is 1.8 minus 2.02, which is going to be negative 0.22. Yep. So this is minus 0.22 times negative 0.1. This comes out to a positive. This is going to be positive 0.022. So we have 1.01 plus 0.022. That's going to be 1.032, if I'm correct. Yes, there we go. So there's our final approximation of f of 1.7. For this problem, we're using Euler's method to figure out f of 1.7. We're starting with this differential equation and f of 2 equals 1, and we have increments of delta x equals negative 0.1. So we're going to have to do this in 3 steps then to get from 2 to 1.7, going by 0.1s. Our first step is to find f of 1.9. And to do that, that's going to be f of 2 plus f prime of 2 times negative 0.1. And it's going to be approximately that. We're just approximating each time. So this is going to be 1 plus whatever f prime of 2 is. F prime of 2, we're going to use this differential equation. We're going to be doing 2 minus the x value that we're plugging in of 2, which comes out to 0. So this is going to be plus 0 times negative 0.1. So 1 plus 0 gives me just 1. Now that we found f of 1.9, we're going to work our way backwards with f of 1.8. That's going to be f of 1.9 plus f prime of 1.9 times our step of negative 0.1. F of 1.9 we approximated to be about 1. And then f prime of 1.9, that's going to be 2 minus 1.9, which is 0.1. So we've got 0.1 times negative 0.1. That's going to be negative 0.01. 1 minus 0.01 is going to be 0.99. And finally, we work our way back to f of 1.7. That's going to be approximately f of 1.8 plus f prime of 1.8 times negative 0.1. Again, the step is not changing here. So f of 1.8, we just approximated that was about 0.99. F prime of 1.8 is going to be 2 minus 1.8, which is 0.2. So we have over here 0.2 times negative 0.1. That's going to be negative 0.02. And then 0.99 minus 0.02 is going to be 0.97. And there it is. For this problem, we're told that y equals f of x is the solution to this differential equation with initial condition f of 0 equals 2. We want to approximate f of negative 0.4 with Euler's method and 2 steps of equal length starting at 0. All right, so if I want to get to f of negative 0.4 and I'm starting at f of 0, to get from 0 to negative 0.4, I have to be going backwards by 0.2 each time. So I have step sizes of negative 0.2. So let me just start by doing f of negative 0.2. So that's going to be f of 0 plus f prime of 0 times our step size of negative 0.2. F of 0, they told me, that was 2. And for f prime of 0, I have to use this differential equation up here. Now I have to be careful because this takes both x and y values to make it work. So we have the x value 0 that we're actually plugging in there, plus we have 2 times the y value that goes with the x value 0, and that, according to this, is the y value 2 because we have f of 0 equals 2. So we have 2 times 2 then, giving me a grand total of 4 for f prime of 0. So over here then we have 4 times negative 0.2. And let's see here. I should probably figure out what this comes out to because I have to match one of these answer choices at the very end. So this would be, let's see here, 8, but I have to move the decimal. So negative 0.8. 2 minus 0.8 is going to be 1.2. And we move on. So we have to go back again by another negative 0.2. That would take us all the way back to f of negative 0.4, which is what we ultimately want to find on this one. So to get there, I need to do f of negative 0.2, which we just found, by the way, plus f prime of negative 0.2 times our step size of negative 0.2. So f prime, or at just f of negative 0.2, that was this 1.2 that we just figured out. F prime of negative 0.2, that's going to be the x value negative 0.2 plus 2 times the approximated y value that we just found of 1.2. So this is negative 0.2 plus 2.4, which is 2.2. So we have 2.2 times negative 0.2. So that's going to be 1.2 plus, let's see here, this would be 4.4, but we got to move the decimal again, so negative 0.44. And unfortunately, I do need to actually figure out what this comes out to match one of these answer choices. So, I mean, I think it's pretty obvious which one it's got to be. If we were starting with 1.2 and subtracting something, it's got to be less than 1.2, and there's only one answer choice that is less than 1.2. And if you think about it, this is kind of like 120 minus 44, which would be 76, except that we have decimals involved, so this is actually 0.76. So that's then going to give us answer choice A. On this problem, we're told that y equals f of x is the solution to this differential equation, which is kind of interesting. We've got 4x plus g of y, and we have the initial condition f of 1 equals 10. We want to know the approximation for f of 1.5 using Euler's with a step size of 0.25, starting at 1. So first we're going to have to figure out an approximation for f of 1. Then we're going to figure out, well actually we'll start with an approximation for f of 1.25. Then we'll go from there to find our approximation of f of 1.5. So to get f of 1.25, we need to do f of 1. We're starting at 1. So we need to do f of 1 plus f prime of 1 times our step size of 0.25. Basically just kind of using a tangent line approximation. Now f of 1, they gave us that. They said that was 10. F prime of 1, well, how do we find that? We have to use our differential equation up here. So that's going to be 4 times the x value 1 that we're plugging in, plus g of the y value that goes with 1. Well, what y value goes with the x value 1? Well, the y value 10 right here. So we're going to really be doing plus g of 10. So this is going to be 4 plus whatever g of 10 is. And we have a table here, actually, that tells us all the values of g that we might need to know. G of 10 in this table happens to be 4. So we have 4 plus 4, which is 8. So this is 8 times 0.25. So let's go ahead and simplify that to make the next few steps of this problem easier. This is basically 1/4 of 8, which is 2. 10 plus that gives us 12. All right, so we've got f of 1.25. Now we move on to f of 1.5. That's going to be f of 1.25, which we just found, approximately, plus f prime of 1.25 times our step size of 0.25. So that's going to be, let's see, f of 1.25 was approximately 12 when we found that earlier. F prime of 1.25, that's going to be 4 times the x value, 1.25, plus g of the y value that goes with this. Now, the y value that goes with this, basically f of 1.25, is this 12 that we just found here. So we're doing plus g of 12. So 4 times 1.25, that's going to be 5. G of 12 up in the table here is negative 9. So 5 minus 9 gives us negative 4. So we have 12 minus 4 times 0.25. This is really 12 minus 1, which comes out to 11. So that gives us choice B.